Okay, good afternoon to everybody joining from Europe and good morning to those joining from the US. So my name is Regina Dittmann and I'm from the Forschungszentrum Jülich in Germany. I'm very happy to welcome you to the webinar about the roadmap of neuromorphic computing and engineering in the new IOP journal with the same name. We will have two invited speakers today who will introduce the roadmap. But before we come to this point of the program, I would like to give the words to Giacomo Indiveri from the Institute of Neuroinformatics in Zurich, who's the editor-in-chief of this journal. So please, Giacomo, welcome to our webinar.
Hello, it is my pleasure to introduce to you the Journal of Neuromorphic Computing and Engineering. I am Giacomo Indiveri from the University of Zurich and ETH Zurich, and I have the honor of being the editor-in-chief of this journal. I am supported by an amazing team of colleagues in the editorial board and by an amazing team of publishers and colleagues that are making the best for promoting the growth of the community and making this journal become extremely successful. It's a new journal, it's open access. There will be publication fees for submitting papers, but for all of the next year, this is being waived to promote the growth of the community. The community working on neuromorphic computing and engineering is really trying to solve some important challenges that standard computing technologies are starting to face. And it has three main pillars. The community is composed of basic research colleagues from academia and university that are looking into neuromorphic engineering for really understanding how the brain works by building emulations of neural circuits. So it's really a fundamental research effort that is trying to emulate neural function using both analog and digital circuits. Another community that is using the term neuromorphic and it is contributing to the growth of the neuromorphic computing and engineering field is the one working on memoristic devices, material science and devices, for building and creating new emerging memory technologies that can be used to emulate the properties of real synapses and therefore to build large-scale and powerful computational brain-inspired neural systems. This community is looking into in-memory computing and high-density arrays, so it's working on very promising areas that could really solve some of these challenges that the computing field is facing. And finally, the most recent part of the community, the pillar, is the one that is looking into applications. It's an application-driven system that is simulating spiky neural networks using dedicated custom VLSI chips. The first one that was proposed was a pure digital spiky neural network chip that is the True North from IBM, but also there are others that are providing impressive results, such as the SpiNNaker, the Heidelberg, and now more recently the Louis chips. And also this community is using the term neuromorphic computing because it's using these chips to really try to solve problems using spiky neural networks. So the goal of the journal is really to bring together all of these communities and support the growth of the community with a really high impact journal that can show the benefits of these approaches. So the idea is really to bridge these multiple communities and to support papers and the publication of papers that are looking into deeply rooted neurobiology and neuroscience, or works that exploit the physics of CMOS and memoristic devices to implement spiky neural networks or artificial neural networks, or also research and research efforts that combine analog, asynchronous, and digital and logic circuits to build alternative new computing devices and new processors. Or finally, looking at also academic and industrial research and groups that are looking into solving practical applications, in particular in the edge computing domain. The journal has already accepted a wide range of publications, of submissions. They're equally distributed between neuroscience, modeling, and material science and devices. It aims to become a really high impact journal. We are really looking forward to receiving your submission, and we're really looking forward to promoting through this IOP journal the growth of the community. Thank you for your attention.
Yeah. Thanks, Giacomo, for giving the introduction to this new journal. So now it's my role to talk a little bit about our new roadmap on neuromorphic computing and engineering. This Giacomo. So this roadmap on neuromorphic computing and engineering is more or less just accepted for publication. It's already available in arXiv, and but we hope that it will be published soon. So this roadmap was initiated by Nini Pritz, and it was edited by Dennis Christensen, Bernabé Linares Barranco, and Daniele Ielmini and myself. So we were very happy that many people contributed from leading research institutions, and they agreed to contribute with their view about the current state and the future challenges of the research area. So the aim of this roadmap is to present a snapshot of the present state of neuromorphic technology and provide an opinion on the challenges and opportunities in these different major areas. So the first area, which is one section of the roadmap, is about materials and devices. And this will be afterwards presented, an overview will be presented by Sabina Spiga. So the second section is about neuromorphic circuits. This will be presented by Steve Ferber. The next section is about neuromorphic algorithm that will be presented by Emre Nefci. And the last two sections are applications and ethics, and the application field will be presented by Chiara Bartolozzi. So the first speaker of today is Sabina Spiga. Sabina Spiga is currently research director at the National Research Council, CNR, Institute of Microelectronics and Microsystems in the unit of Agrate Brianza in Italy, and her main research activities devoted to the development of oxide-based resistive switching memories and memoristic devices for neuromorphic systems and novel computing paradigm. So please, Sabina, the stage is yours.
Hello to everybody, and my name is Sabina Spiga. Good morning, good afternoon, good evening, depending on your time zone. And it's a pleasure to be part of this online webinar. And today I would like to briefly discuss the contents in terms of material and devices of the roadmap on neuromorphic computing and engineering. As you can see from the index, the roadmap discusses the current status and challenges and perspective of several technologies, from the most established one to emerging ones. And for sake of time, I will briefly discuss some of them. I would like to start with this slide to mention how there is today a large effort and research worldwide to develop neuromorphic devices that can be used as a building block of new computational architecture inspired by the brain functionality. This research spans from new materials and physical phenomena which can enable the fabrication of nanoscale functional memory stick devices. And these devices can be used to expand the functionality of current CMOS circuit and system used for neuromorphic application. And also we can exploit the dynamics of these new devices to compute with dynamics. And I would like to mention how is important also to develop the technology in a holistic view together with the concept from neuroscience and machine learning, and to take real advantage of this interdisciplinary community which is growing up around the field of neuromorphic computing. I will now discuss a little bit about resistive memory. Resistive memory have reached today a good maturity at technological level thanks to a large effort and research at both academic and industrial level in the last 20 years. And especially I mention and I show here a few of the most advanced memory technology: resistive RAM, phase-change memory, MRAM, and ferroelectric FET. And thanks to their maturity, and most of them are already in production or close to production, there is really plenty of opportunities for this technology to be used for in-memory and neuromorphic computing. Indeed, thanks to their properties, most of them have been already exploited also for circuit and systems. Close to this technology, there are also a lot of several emerging neuromorphic material and device concepts as shown in this slide and discussed in the roadmap. I would just mention the nanowire network, for instance, for reservoir computing, 2D materials and van der Waals heterostructure, organic materials and device-based organic materials, and also emerging spintronic concepts that go beyond the more standard magnetic RAM memories. I would like now to discuss more into detail resistive RAM technology, which can be divided in balance change memory and electrochemical metallization cell, depending on the switching mechanism. But resistive RAM really collect together a large class of non-volatile memory concept based on a resistor as a memory element that can be programmed in 2 or more states. And all these devices are very compact. Most of them are 2-terminal or also 3-terminal devices has been exploited. And the physics beyond this is to exploit electrochemical and nanoionic redox effect in various material systems. For instance, transition metal oxide, chalcogenide glass, metal doped perovskite, and also conductive polymers. As you can see in this graph, also these devices are quite compact, can be integrated in high density array, either in a cross-bar integration or 3-dimensional stacks. I will now focus more on balance change memory. And this slide summarizes briefly the various types of balance change memory under study. As you can see, there is not just one device, but is a plethora of different devices. On the left, I show the filamentary switch, which is the one representing the most advanced device at technological level, and which exploited the anion or cation migration for ECM. And indeed, you can control the device conductance by the formation and dissolution of local filament made of defect shorting 2 electrodes. These concepts are quite advanced, and most of the more promising applications in terms of circuit have been shown by using filamentary devices. But I would like to mention that there are other concepts that are very appealing, especially toward, for instance, analog control of switching, namely in the interfacial or recently proposed bulk switching in the redox transistors. All these devices use several different types of materials. Regarding the function that has been implemented in balance change memory, they can be used. Originally, they have been studied as binary memory for storage, but when using these devices for computing, is also possible to address other functions, and they have been proposed to implementing, for instance, the synaptic node in artificial neural network or spiky neural network, also by exploiting the multi-level of analog capability and also the stochasticity that we can achieve in their programming. For instance, below I show various examples of a function implemented by filamentary Aphium-based balance change memory. On the bottom left, you can see how in the same device it's possible to have binary or multi-level switching. In this figure, you can see how we can control the conductance variation through a set of train of identical pulses, or we can even engineering a specific level through program and verify scheme. And in this last graph on the right, bottom right, you can see how we can also use the stochasticity to implement some programming strategy. Moreover, this device exhibiting a large dynamics and plasticity dynamic, which is important for training in network, artificial neural network or spiky neural network, and this accumulative behavior where there is a device response which depends on the number of incoming spike of pulses, and that could be, the dynamic could be linear or non-linear, symmetric or not symmetric. And you can see on the bottom a few examples of how we can achieve this dynamic in filamentary valence change memory, interfacial or bulk resistive RAM. And you can see that we can maybe solve the problem of filamentary switching, where we have a large variability and stochasticity, using interfacial resistive RAM or even this redox transistor recently proposed. Finally, it's also important to address the retention dynamic to achieve this longer short-term memory effect. Usually, it's quite easy to achieve a long-term memory with using valence change memory. It's not so easy to achieve short-term memory, but has been proposed, for instance, in interfacial devices, this volatile tungsten-based memory store and other material systems are under study. And of course, you can use also ACM type of memory to achieve this short-time effect. Just to mention that all these dynamic properties of the device are really beneficial for implementing in neuromorphic computing schemes. In this slide, I would like just to summarize briefly what is the current status and open challenging for the valence change memory devices. The one I discussed, I mean the filamentary interfacial and redox transistor. This graph just to show that currently the best performance are achieved by filamentary devices, but this is only because their technological level is more advanced. Then maybe in the future you can see that also interfacial devices or redox transistor will play a major role, and they can help really to go towards analog memory or to exploit some more dynamics towards volatile devices. You can see in this graph on the right that all these emerging resistive memory are now reaching a good maturity in terms of performance, but also cost, which is important for application. And I would like just to comment that today no single memory device is okay and is a unique choice for neuromorphic computing, because we still have different requirements for artificial neural networks, spiky neural network, for inference or training. And still there is a lot of research to do to identify the best solution. And beyond valence change memory, I would like also to show another example, which is discussed in the roadmap. Phase change memory are devices quite established and into production. And also in these devices, it's possible to achieve all this interesting behavior. For instance, beyond the standard non-volatile binary stager, we can engineering analog or multi-level storage, which is, for instance, useful for matrix vector multiply operation. And also we can exploit this accumulative behavior, which is useful for neural network training or emulation of neural and synaptic dynamics. Of course, also in this case, as previously discussed for valence change memory, we have some kind of stochasticity and non-linearity, which in one side could be detrimental, but on the other side can also be used for computing. Then to summarize and to give an outlook, there is really plenty of opportunity to use nanoscale emerging memory still neuromorphic devices, and we discussed this in the roadmap. Research and development are still needed at all levels, from materials to device physical understanding, and also how to use this device for computing. And in the future, I think heterogeneous systems with multi-component are expected to play an increasing role. And thank you very much for your attention.
Yeah, thanks a lot, Sabina, for this nice overview on this section of the roadmap. So the talk is open for questions now. Please feel free to submit questions into the chat. So in the meantime, I have one question concerning this 3-terminal devices, this bulk type of switching. So it often seems like those devices are more linear, perhaps even more linear than this interface type of devices. Do you have any idea why they are more linear than the 2-terminal devices, or is it good luck? So, but I have seen this often, that they look quite linear.
Okay, I mean, is quite complex because, I mean, these devices are not just 3 devices, but is a plethora of material system. And I would say that also with programming strategy is always easy to engineering different linearity. But we also recently published some work also with other group. Depending on the application, linearity is not always a requirement. For instance, for spiky neural network, nonlinear system can help to avoid catastrophic forgetting and to improve the memory lifetime. Of course, for deep neural network, we really need some linear update. But I mean, the physics behind the device is not pushing for linear. What is nice in this new proposed 3-terminal bulk or redox transistor is that the switching is due to the bulk, is changing the conductance of a channel through ion intercalation of oxygen ions of other elements. And indeed, there is more chance to at least limit the stochasticity due to the bulk switch instead of filamentary one. But you can find in literature many data also with nice linear data for filamentary devices.
Okay, any idea about the kinetics of these 3D bulk systems? Do you have any idea what is the speed limiting step there?
From the published result, from other group is not my work. The kinetics seems to be quite fast, then similar to the other devices. If I remember well, they already demonstrated the switching time in the nanosecond range.
Okay.
But there are few works, then I mean there is still room to improve them.
Okay, so I'm still waiting for question. There was a question from the audience who asked if the video will be available after the talk, so I can answer this question. That holds for all presentations today. We will send out the live recording. The webinar recording will be sent automatically to the participants after the event. So there's also obviously another question on the. Okay, so now there are some more questions. Okay, so there's a question from. Yeah, that's not clear. I'm looking at the questions. Okay, I have to orient myself on the questions. So there was one comment or question. Okay, now I understand this. So there was something on the also on the redox devices. Array integration was shown to be low compared to other technologies. Is this a fundamental limitation, or is there room for improvement? I think that's a question to you,
Okay,
Sabina.
thank you for the question. It's a very important question. I would say that for filamentary redox devices, the array integration has been demonstrated and is quite good. I think the only best technology is phase change memory. For emerging technology, it's true that the array demonstration still have to be demonstrated. I think, yes, there is room for improvement, but filamentary resistive RAM are already there, and many chips have been demonstrated with comparable result to PCM or ferroelectric memories.
Okay, thanks. There's another question asking about the switching speed. Some of the literature suggested millisecond regime for the programming. Isn't it too slow for actual AI applications?
Thanks for the question. I think these specific devices, I mean, you can find switching time of over several order of time scale for all this plethora of devices. Anyway, I would like to comment that even if we have slow devices, for some neuromorphic application can be indeed interested as well. Especially if we would like to engineering systems that are able to track sensor signal in real time. We don't need fast devices.
Okay,
then
so there's a last question about the asymmetry. So linearity might not be essential, but how about the asymmetry between potentiation and depression?
Asymmetry is very important indeed, because otherwise you have to use some correction strategy during your algorithms. But yes, there is room also to improve this aspect in terms of developing new material or new devices or programming strategy.
Okay, thanks a lot, Sabina. The time is over. We have to proceed now to the next presentation. Thanks a lot for you and also for the questions in the chat. So I think we have to move on to the next speaker, who is presenting the part about neuromorphic circuits. This is Steve Ferber. He's professor of computer engineering at the University of Manchester in the UK. He leads the SpiNNaker project, where one of the two human brain project large-scale neuromorphic computing platforms were developed. So please, Steve, the stage is yours.
Okay, thank you very much, and hello everybody. I'm here to talk about the section of the roadmap on neuromorphic circuits, and I'm going to focus on the large-scale neuromorphic computing systems part of that section, because that's the bit I was involved in drafting. But before we get onto large scale, it's worth reminding ourselves that neuromorphic engineering computing really has its grounding in the 1980s at Caltech, where Carl Vermeer first introduced the term, and he observed that there was a close analogy between the equations that describe the flow of ions in ion channels in neurons and the equations that describe the flow of carriers in subthreshold analog transistors. And he used that analogy to build subthreshold analog electronic circuits that had behaviors that closely matched those found in the biology. And in the 80s, his group at Caltech went on to develop impressive sensors for touch, for hearing, and for vision. And we all are building in one way or another on the foundations of that early seminal work. Now, the work I want to describe here comes quite a lot later, and has been supported over the last decade by the European Human Brain Project, which is a large-scale flagship project with over 100 universities focused on many different aspects of brain science. And the question, why focus on the brain, was raised early on, and the Human Brain Project offers these three answers to that question. Firstly, understanding the brain remains one of the grand challenges or frontiers of science. We still fundamentally don't understand how this organ, upon which we all depend so critically, operates. But so that's a pure science question. The second question, second reason, was understanding diseases of the brain, which cost the developed economies a huge amount. I mean, more than cancer, heart disease, and diabetes put together in terms of their annual economic cost. And of course, alongside the economic cost is the quality of life impact on those affected and their families and friends. So addressing diseases of the brain is a huge problem, and that's difficult because we don't understand the brain. So those two reasons are closely linked. The third reason was with the objective of developing future computing based to a greater or lesser degree on what we do understand about the brain. And that really is where neuromorphic computing comes in under the future computing heading. And here work in the HBP has focused on neuromorphic machines and on algorithms and architectures for neuromorphic computing. There's been quite a lot of important work on the theory underpinning building neuromorphic machines and also on the applications that those machines might find. Now, within the Human Brain Project, there's been support for two different lines of large-scale neuromorphic engineering. The SpiNNaker machine developed by my team at Manchester works on the basis of many core emulation, so it's really a large-scale computer with some features that are tuned to the brain modeling application. And the second large-scale system is the BrainScale system developed at the University of Heidelberg in Germany, which in many ways is much closer to Mead's original concept of building electronic circuits that model the behaviors of various features of the brain. And you can see in the pictures here that both of these machines have been built to scale. The SpiNNaker machine has 1 million processor cores arranged across those 10 rack cabinets, and the BrainScale's machine uses wafer scale integration, and whole wafers are integrated into those modules, and there are, I think, 20 of them across that machine. So two very different approaches. The many core architecture supporting massively parallel simulation of brain systems, and the wafer scale analog circuits operating in a physical mode and emulating the way the brain operates more closely rather than simulating it. And for both of those machines, the HBP has also supported the design of second generation machines. And I'll talk a little bit about the second generation SpiNNaker machine shortly. Both of these platforms have in common the fact that they were designed and built by their respective teams from the transistor up. Now, of course, there are many other neuromorphic computing systems around the world, and there are some others at large scale. And if you look at the larger scale systems, then you can arrange them from left to right on this picture in terms of increasing biological realism. So the way they function is closer to the biology as you go from left to right. And if you like, their programmability or ease of use increases as you go from right to left. So there are many different points on this scale, and the SpiNNaker system really represents the extreme left-hand end of the scale. The Heidelberg system is pretty much to the right end, and other systems that are notable, such as the IBM True North and the Intel Loihi, are somewhere towards the middle of this scale. They are both digital systems, but with the algorithms that they use embedded in the hardware, whereas in SpiNNaker they're implemented in software. So if we look at the example that I'm responsible for, which is the SpiNNaker machine, we started by designing a chip, and in the package there are in fact two chips. The lower lighter colored square chip is the compute layer, and the darker rectangle on top is industry standard memory, and those can be packaged, and then those packages can be arranged on a 2D surface of almost unlimited scale. We choose this circuit board as our basic unit for building large-scale systems. This board has 48 SpiNNaker packages incorporating 864 processor cores, and that's then been used to assemble the large-scale SpiNNaker machine in Manchester, which since November 2018 has been offering a service openly under the auspices of the HBP. In fact, it's been running since April 2016 at about half that size, and we have a few hundred remote users and several million jobs have been run. So it's a fairly widely used service, and there are about 100 other SpiNNaker boards in various labs around the world. Now, of course, at the low level, what's executing on this machine is real-time software running on these small ARM cores in a massively parallel configuration. We don't expect our users to understand how to work with that kind of low-level technology. So we have a software stack which enables users to describe their problems in a standard language, and the one that most of our users use is Pine, also developed within European projects and supported within the HBP. Pine simply stands for Python Neural Networks, and it's a Pine library that supports concepts such as populations of neurons and projections from one neuron to another. And you can write the description of your network in Pine. You can run it on your laptop using one of the standard software simulators such as Brian or Nest. And then you can feed the same Pine description to our software stack, where it's processed and mapped onto the SpiNNaker machine through various layers of software such as SpiNNaker and Spin Front-End Common. All the issues of mapping the problem onto the machine and setting up the routing tables to connect with the processors appropriately. Those issues are all handled by the software stack, and the results come back to the user in the normal way. So the goal here is to make the use of SpiNNaker as transparent as possible to the regular user of Pine. And that's the basis of the service we offer through the HBP. Now, we've been developing a second generation system. The SpiNNaker technology offered through the HBP is now almost 20 years old, and using a more up-to-date technology, we can scale the system. And with the SpiNNaker 2 chip, which we've co-developed with the Technical University of Dresden, we can now offer 152 cores on a single chip. So that's approaching 10x. And of course, we have to scale all the other system parameters accordingly. This chip has been in development for several years. It's based on a unit we call a quad processing element, and you can see that QPE is tiled across the chip. The QPE has been fully laid out and fabricated on prototype chips and tested. And in fact, now the final SpiNNaker 2 chip has just recently come back from fab and been evaluated in the lab and is pretty much ready to go. In the course of building these machines, we've learned quite a lot about what's necessary to support large-scale systems of spiking networks, and SpiNNaker 2 incorporates a lot of that knowledge into its base technology. So if we look at the processing element, we have very flexible power management. So each of the 152 processing elements can operate at a different DVFS level in each of the time steps. In other words, we can change the DVFS level at 0.1 or 1 millisecond time steps. We can analyze the workload for the next time step and then configure the processor to operate at its highest efficiency for that workload. We've added considerable support for memory sharing, which is a bit difficult on the first SpiNNaker machine, and we use it a lot more than we expected when we designed that machine. SpiNNaker 2 also has multiply accumulate accelerators so that we can support conventional machine learning algorithms as well as neuromorphic or spiking networks. But we've also introduced accelerators for those spiking networks based on what we've learned from observing the way users operate on the current machine. And everything's connected as usual these days through a network on chip. And at the very lowest level, we have sophisticated ways of adjusting the technology as it comes out of manufacture to reduce the variance in proportion to the mean in terms of performance and power efficiency. So that's a low-level technical slide, but it's indicating the kind of lessons we've learned in the last 10 years of running the SpiNNaker 1 machine. So to conclude what I want to say about large-scale neuromorphic computing systems, there's more said in the report when it comes out, but they're in a position where we can offer reliable, well-supported services to a wide user community. They're openly available to anybody who wants to use them around the world. They're supported by stable software stacks, and these abstract the users away from the lower level details unless the users really want to dig around in those lower levels. And so users can really focus on the kind of services offered by the Pine language, on network architecture, on learning rules, on brain modeling, or on engineering applications. The machines are available to train the next generation, to prepare them for the sort of neuromorphic technologies that will be coming in the future. And they offer a flexible development platform for exploring the neuromorphic computing space. So the sort of devices we heard about in the first presentation can be modeled on SpiNNaker, and SpiNNaker can be used to explore how those devices might perform at system level, while those devices are still in development in the lab and in production facilities. And that much is already established. And now the second generation systems are beginning to emerge, and they will raise the performance that can be supported by an order of magnitude in the next step. So I will finish there. Just a note, if you're interested in learning more about SpiNNaker, the team put together a book last year, which is open access, so it's free to download, or you can pay money for a paper copy if you want to. Otherwise, I'm ready and happy to take questions.
Yeah, thanks a lot, Steve, for this impressive presentation about the SpiNNaker. So there's one question in the chat asking how do you believe that we could be able to use these technologies in the future to replace parts of a damaged brain?
Well, so brain-computer interfaces are not really my subject area. I mean, I think there is research going on looking at replacing damaged functions. Of course, one well-established approach is the cochlear implant, which is already in widespread medical use. Less advanced, but still being developed, are retinal implants. Both of those are effectively replacing neuromorphic sensors with electronics. Now, how much further that can go, I think you would need to ask somebody who is more working in that territory than I am.
Okay, so there's another question from Sebastian Siegel. Where, if any, do you see opportunities for memoristic devices to support large-scale neuromorphic systems, such as SpiNNaker and BrainScale? Can they be used as data storage, or even the specific memoristic dynamics be directly employed?
I'm sure that is possible, yes. I mean, I think the developments in novel neuromorphic inspired devices are very interesting. But of course, before you can use them in a large scale system, they have to be available in large scale production. And it's a big step from having a novel device working in the lab to having it working in production, where you can manufacture billions at once and be fairly sure they'll all work. And you can control the variability from device to device and so on. These are the kind of things that we now take for granted in conventional digital CMOS. Making a billion things on a chip and expecting them all to work is the normal state of the art. It's still a fairly big challenge for the novel device technologies.
Yeah, so let me complement this somehow, this question. So where do you see the need for having new hardware? I mean, at the moment you're extremely happy with using SRAM and DRAM. So if you would have a wish for new hardware, what would you like to have?
Well, I think in a sense the questioner is right that that when we're working in software in particular, we can model anything. So we don't actually need a memristor to use a memristor model on a machine such as SpiNNaker. But we're also interested in applications, and there's growing interest in the convergence of neuromorphic technologies and mainstream AI and machine learning, and therefore applications such as edge computing. What we really need to do is to get the neural network density up as high as we can in terms of number of neurons and synapses on a chip, whilst keeping the power consumption as low as we can. And I think that's one area where novel devices could help quite a lot, because in a regular compute system, accessing the memory is one of the significant consumers of power.
Mm-hmm. Okay, so thanks a lot, Steve. I think due to time reasons, we have to move on. Thanks a lot for the presentation. And we will now move to Emre Nefci, who's the director of the PGI 15 Neuromorphic Software Engineering at the Forschungszentrum Jülich. He's also affiliated to the RWTH Aachen and to the UC Irvine. Emre is interested in understanding the bridges between models of computation, brains, and hardware. So please, the stage is yours.
Okay, excellent. Thank you, Regina, for the introduction. So I'm going to focus on the neuromorphic algorithms section of this roadmap. And essentially what you've seen right now is the different kind of technologies that we can use to build neuromorphic systems, so be it digital, using memristors. There's several technologies out there which raise new opportunities to building computing systems, and in particular, those computing systems that operate on local information, that use the physics of the device, like the brain. Now, when we have these systems, they also raise certain challenges, which is that how can we actually connect the dynamics, the properties, and the constraints of these devices to actual computations and to actual algorithms. And understanding this is really key to map and deploy these neuromorphic systems in real-world problems. And so that is really the subject of that section of the roadmap. And of course, it's very natural to take inspiration from brains to do this. Of course, as we've heard from Steve Ferber earlier, the whole inspiration for neuromorphic engineering comes from neuroscience, and the understanding that the laws that govern the ionic currents are not so different from those that govern electronic currents, and that somehow this also may extend to these novel devices. So in that analogy, it turns out that the brains operate with dynamic, noisy, and local information, a bit like the devices that we are trying to build. And so it makes really sense to continue this pursuit of understanding how the brain works in order to build these neuromorphic circuits and build the algorithms for them. And in this section, so of the computational neuroscience is put really nicely. The goal of computational neuroscience is really to take the principles, to distill these principles into a set of rules that we can then apply into our neural systems. Now, those rules may, of course, account for the architecture, the dynamics, and so on. But they're all based on a key concept, which is that neurons communicate with each other using all or none events or spikes. And that immediately raises the question, well, if that is how neurons communicate, if that is the medium by which neurons communicate, how is information encoded in those spikes? And Simon Thorpe in this section is describing different methods of encoding this information, whereas a simple method would be just encoding, for example, a number in the a value in the number of spikes that occurred in a time step, or using, for example, the precise timing, or even the more elaborate methods by which we look at which of a group of neurons were active when during a certain time period. And this way we can encode information in a very efficient way by making use of this of the spikes of the neurons. Now, this link to neuroscience is very interesting, but it's very tedious and difficult to understand how we can assimilate all this information that comes from neuroscience with our models of computation. And just understanding that question first requires positing and making hypotheses of what is a good model of computation. Now, that is a question that if we try to address it in its entirety would take us all day. But in this particular roadmap, so there are three examples that I think are very well selected because they're often used in the community. So one model of computation is called reservoir computing, which started with liquid state machines and echo state machines. The idea here is really that there's a physical dynamics in our system and that we can build readout circuits that are trained to select which of the components of the system to read out in order to fit a certain output. And the advantage of this is that we don't need to understand exactly what's going in that physical system. We only need to be able to read from a subset of it. And so this incorporates nicely the idea of the temporal dynamics of brains. On the other hand, we have John Tapson, who is describing the ideas of stochastic computing. So having a system that is inherently stochastic allows us to do computations that we otherwise can't do and in very efficient ways. In this very simple example, for instance, you can encode a multiplication here by simply using this AND gate and sending in these stochastic events, so on and off events, which are not unlike spikes, of course. This is one way of doing stochastic computing. There are several other ways of doing it, which you can relate to probabilistic inference. And we know that brains are, at least to some extent, doing some approximate probabilistic inference. And a very rich and growing field now is also doing deep learning with spiking neural networks. And here, in this very basic idea, that what you can do is just replace one of the ReLU neurons in your network with these leaky intergonial fire neurons and train the network either end-to-end using these spiking neurons, or first train them in the artificial neural network and then convert the parameters into the spiking neural network. And this leads to obvious applications that we'll be hearing later from Chiara Bartolozzi in the fourth section. The reason why I like these three models of computation is that you can mix and match them. So in several of these models of computation, we use either explicitly or implicitly the ideas of reservoir computing in order for training, as well as stochasticity, because our devices, our systems will have that inherent stochasticity. And a key method, and something that of course occurs in all of these computational models, is that we need to train and learn from these systems. So in the brain, I'll do a very quick 1 minute primer on plasticity. So plasticity in the brain occurs when the neurons tend to spike in coincidence. They increase their weights when the presynaptic and postsynaptic neurons fire one after another, and generally, but not always, they decrease in the other order. And so this can easily be captured by a certain rule that's called spike timing dependent plasticity, where the information of the timing when the spiking occurred is stored at the synapse of the neurons. And here immediately you see, well, the volatile devices that we've been seeing, for example, in Sabina Spiga's talk, are really key to implement these temporal processes and enable learning, as well as, of course, the non-volatile devices, which would implement the weights and store the weights over longer time periods. The very attractive feature of this learning paradigm is that it only operates on local information. If you remember, that's one of the key features of how brains compute. They make use of local information because it is a physical system. So what we also find is that it's useful to add in additional information that just comes from elsewhere that is representative of the performance on a certain task. And you can see this as like a third modulating factor that changes how the weights are going to be updated. And interestingly, these kinds of rules can be made compatible with gradient descent, hence these spike-based deep learning models of computation. And there are several work now that builds on these ideas of we call them surrogate gradients, because you need to do certain approximations that result in a surrogate network. And we arrive into a setup where we can actually start doing learning in spiking neural networks and the associated neuromorphic hardware. And there's several setups for this kind of learning. Of course, the most natural setup is where you have a neuron in its plasticity dynamics co-located, so essentially in the same place. This is a very similar, of course, to how the brain works. The neurons have their own plasticity mechanisms occurring locally. But this may not be the best option for neuromorphic hardware in all cases. Sometimes we'd like to have an external processor that performs learning. So here you would have, for example, the learning processors that would feed in their information to the chip, and then that would feed back the states for making updates. So we call this the chip in the loop approach. Or there's also the offline training, where you train a neural network off chip on a computer, and then you map the parameters to the chip. And all these different approaches are complementary to each other. First, if you're training off chip, you have all the power that a supercomputer center can offer, but you're limited in how quickly you can make an update. Whereas if you're operating locally, well, you're doing this in a very efficient manner. You can do it in continuous time. But of course, this limits the extent of how much you can learn, just by the fact that you're limited in data and you're also limited in power. And so these different types of learnings feed into each other. I'd like to also point out two different, I think, important features, since this was the section that I was responsible for. I think so the software and hardware are going to, conventional software and conventional hardware are going to play key roles in actually programming this hardware and these learning systems, as well as kind of pre-training these networks. So priming the networks for learning, and because this will allow the local plasticity then to make only a few updates in order to reach a desired behavior. And this comes very nicely with, I think, one of the most impressive features of the brain. It's its ability to learn things quickly. You might have seen this figure if you're in the neuroscience community. So if you see these figures in these red boxes, which are arbitrarily called tufas, you have no problem in finding the other tufas in this figure, even though you may have never seen these objects before. So we learn extremely quickly to generalize. Of course, this comes with, this is possible thanks to our baggage of knowledge that we have prior to basically seeing this problem and these new objects. And this is exactly the kind of things that can be achieved using these different types of learning so far that I've discussed earlier. So Franz Scher and Wolfgang Maas describe, for example, this approach of learning to learn, where you have both an inner loop and an outer loop of learning, where the inner loop, this would be, for instance, what would happen in your neuromorphic device as it's in this environment. And you can optimize how well this learns in an outer loop. And this would happen, for example, in the conventional computer. Once you've optimized this, you can map the parameters onto the chip and do fast on-chip learning. And it turns out that we're actually doing this using a so-called gradient-based meta-learning, and we're able to pre-train these spiking neural networks in ways that even sometimes exceed the performance of conventional neural networks. This we're actually going to submit just in a couple days to this journal. So I'd like to just very quickly summarize. So the TLDR here is that, so we have these novel materials and circuits which raise new opportunity and challenges for neuromorphic computing, and we can really take inspiration in how the brain computes for building these novel neuromorphic algorithms. And so this training and learning are really the key components for neuromorphic circuits. And thanks to all the devices progress here, we are able to improve how that is occurring both in offline and online training. Okay.
Yeah, thanks a lot, Emery, for giving this very nice overview on this section of the roadmap. So yeah, we are waiting for questions from the chat. So please put questions to Emery in the chat. So meanwhile, we are waiting. We have one question concerning STDP. I mean, you clearly said you need volatile devices to have a useful learning rule, STDP-based learning rule. But if you have a look in the literature, you find hundreds of papers of people using non-volatile devices and showing STDP by overlapping pulses. So what do you, what is your opinion of this? Do you think it can be useful, irrespective of that it does not really contain the time information?
That's a really good question. Actually, overlapping pulses means that the pulses need to have some temporal extent, right? And so in some ways, the trace that is required for STDP is embedded in the temporal length of that pulse. It turns out that if you would like to do gradient descent, which works particularly well, you see that you need to have longer time constants. The time constants of STDP need to correspond to the time constants of the neuron, which can be tens or hundreds of milliseconds. And so making those pulses hundreds of milliseconds may not be the best approach. Plus, and we see this both in our theories of the surrogate gradients and also EPROB from the Wolfgang Maas group, it turns out that you require a trace that is specific to each synapse and not each neuron. And so this precludes that idea of using the presynaptic and the postsynaptic pulses as the carriers of the trace.
Okay, so thanks for your answer. So I think here is one question from Matthias Borg. So how deep should SNS be for efficient STDP learning? Since live neurons act as integrators, the number of spikes in the deeper layers will be lower and maybe not sufficient for proper training.
That's correct. So there is a very important requirement for initializing these networks properly and for propagating the information from layer to layer. When we train these networks, we really need to start in a situation where a small or that changes in the input actually make changes in the output. So we have a signal for learning. Now, in STDP, this can be slightly different because in STDP, you can make a meaningful update or close to meaningful updates in the absence of feedback from the network's performance, in which case there's less of a requirement on this initialization. So I guess it's on a case-to-case basis here on how deep the network should be to answer the question. The important point to make is that STDP does not solve the credit assignment on its own because it only uses local information. And so depth, you can make your networks deeper, but it's not necessarily going to make your network more accurate. On the other hand, if you use these surrogate gradient approaches that make updates based on the like we have here, based on high-level inputs, then of course you need to find clever ways to propagate this information back to the neuron, and that is a matter of research.
Okay, thanks a lot, Emre. Due to time reasons, we have to. Oh, that's one question, but I think we have to. We will answer all the questions by email afterwards. But I think we have to continue due to time reasons. So thanks a lot, Emre, for this nice presentation. And we will now move on to Chiara Bartolozzi. Chiara is principal investigator of the event-driven perception for robotics research line at the Italian Institute of Technology in Genoa. Here, her main expertise is in neuromorphic engineering applied to humanoid robotics, focusing on event-driven vision and touch. So please, Chiara, the stage is yours.
Thanks, Regina. Can you hear me?
Yes.
And see my slides?
Yes, everything. But you could
Good.
go to the presentation mode.
Sure. Okay,
Yeah.
here we go.
Great.
So thanks a lot. My duty and honor here is to present the last part of the roadmap that is about the neuromorphic computing and engineering applications. We have heard before about all the hardware, the platforms, and the computation that can be done with neuromorphic computing and engineering. Applications is basically taking neuromorphic sensing, neuromorphic computing, and actuation towards the development of autonomous devices. So I have kind of tried to put together all the contributions in this roadmap about the applications. And well, first of all, we have applications mostly in terms of sensing. We have vision, olfaction, audition. We can also have touch, for example, all trying to replicate how biological systems how biological systems perform the acquisition of information from the environment, and using this information to develop efficient systems to extract meaningful quantities that can be used for applications. And in terms of applications, for example, we have self-driving cars, robots, and collaborative autonomous systems. And sorry, but the slides are going by themselves. I don't know why. As I was saying, we can use this type of sensing and neuromorphic computation in applications where you need autonomy. You need to take information from the environment and from the system to take decisions. For self-driving cars, for example, you have to do it online very quickly and robustly, and that applies also in robotics and in collaborative autonomous systems. And then another very promising application of neuromorphic engineering and computation is the medical domain. So in the roadmap, there are a few examples. For example, the use of electromyography and development of small wearable devices that can interpret the EMG to drive prosthetic devices, for example. And then we have the possibility to develop biohybrid systems for preparing the brain. And I put here also in this context the assessment of time series done in an embedded device that is usually or finds a lot of application in the analysis of biological signals like EEG, EMG, that can give an idea of the state of the patient. This was spoiled. Sorry for this thing of Excel going by itself. I tried to make a word map of the content of this part of the roadmap, and the words that kind of pop out are, for example, can and will. We used a lot these words while describing the system of the applications, because we are mostly in a proof of concept stage. We now have platforms, but there's a lot to do to bring this proof of concept into a small device that can be embedded. And so the chapters that you will see in this roadmap will really try to find which are the components, the challenges to get to the next stage that is not just a proof of concept. The other keywords that you can see are hardware, devices, power, and efficiency. And this leads to embedded systems. So as you heard also before, the idea of neuromorphic engineering is to really create devices that are more performing in terms of power, efficiency, size, with respect to traditional von Neumann computing. And this is also enabled by the concept of in-memory computing, where we don't have to transfer data from the device to the memory to do computation and moving back and forth information that is very costly. Other keywords are learning and different processing and models. This leads to the concept of adaptation and generalization. All the embedded systems that we are talking about here are systems that somehow need to interpret noisy data from the real world, from an uncontrolled environment. And to do this, we need to have similar skills as the brain does. So being able to adapt, being able to generalize information, and these are all the concepts that Emre has explained a few minutes ago. The other words that you can see here are sensors, audio, vision, EMG. What is really important in neuromorphic engineering is how you acquire the information from the external world. And therefore, the kind of the root of the system is really in which systems we use and which strategies we use to acquire information. Then once this information is encoded, we can use neuromorphic computing to take decisions and devise systems that are autonomous. So in the perception I mentioned, you will see examples in vision, and this is kind of a very nice concept. You see here a video of an event-driven vision sensor or a neuromorphic sensor, where you see that the pixels are active only when there is motion, only when something happens in the scene, and they have a very high temporal resolution. So this is what I was meaning before, a very efficient way to encode the information, having very high temporal resolution, and this is useful in many applications. However, the main roadblock there is the fact that the information is encoded in a different way. So this is an advantage, but it's also a disadvantage when you want to interface with industrial systems, with robots that are used to a very different way of encoding information, that is a frame. Besides improving the sensors and the efficiency, their filling factor, what is really needed is to kind of have a breakthrough and a change in how people think about computation and how to devise systems that can extract relevant information from these sensors. And this is mostly using spiking neural networks and spike-based learning. The same applies for audition. So here we have cochleas that basically transform the auditory signal into spikes, and the same applies also for olfaction. So the idea here is really understanding from the brain, having efficient encoding, and then devising methods to use these signals to kind of gather information for the behavior of autonomous agents. So this refers on one side to robotics. So what we can do, for example, is take a humanoid robot like the iCab, as we do in our lab, and integrate event-driven vision, audition, touch, and computation to have the robot taking autonomous decisions on how to behave and what to do next. And here the challenge is really to go from the perception side to the actuation side, and do that with a complete full neuromorphic system. And there are a lot of challenges there, from the perception to the computation and to the actuation, also how to combine different systems to get the coordinate behavior. Another example of using vision sensors in this case is the development of self-driving cars. So here is kind of a diagram on the expectations of what autonomous cars could do, from no automation, so only the human driving and the human driving monitoring the environment and taking decisions, up to having full automation. The idea is that since neuromorphic systems have the promise of showing the capabilities of human decisions, because they can have better perception, they can better generalize and adapt to very different situations, and extrapolate a certain behavior from the experience. Neuromorphic engineering and computation is a promising approach to and self-driving cars as to any system where it's really required to have human capabilities. Another example is collaborative autonomous systems. Here, basically, you have autonomous agents. They can be robots, but also other types of intelligent agents. They have to collaborate among themselves and with humans. And here, what is really important is to, again, observe the state of the agents, observe the internal state of the actor, and observe and understand humans in a way to correctly plan for a correct action, and execute these actions in coordination with other agents. And this kind of increases the level of complexity. Also here, what is needed is really to be able to adapt to very different situations and be robust. And this is something that can be enabled by using neuromorphic engineering. Finally, the last kind of topic of applications, the last domain of applications is health. I wrote here edge for health because I think it's really edge computation, embedded and wearable devices where neuromorphic engineering can really bring benefits. Here, we have different types of sensors. We have sensors that monitor parameters of humans. In this case, for example, you can monitor electromyography, so the activity of muscles, to infer the activity of motor neurons that drive our muscles. And if you can infer the activity of motor neurons, you can, for example, infer the intended movement of a person that might have a prosthetic device, like a prosthetic limb, a hand, that you can control by using EMG. And this would be nice because you can have surface EMG, where you really record surface activity from the skin related to the muscles and to the motor neurons. And here, there's a roadmap suggested on how we could do this. First, transform EMG data into spikes and do spike-based learning of the intended motion. But it's also nice to have a look at the decomposition. So decomposition is a strategy to extract information of single motor neurons from the EMG, usually from high-density EMG. And it would be kind of the development would be to find ways to do spike-based decomposition so that we have the spikes directly of the real motor neurons that we are recording for driving the motor, the prosthetic device. And then this goes towards miniaturization and the idea of having electrodes, and each electrode has its own small device that does this EMG decomposition and movement classification, so that you can have a very low power wearable device that you can use in prosthetic applications. As I said, there's a chapter on the use of time series. So neuromorphic, since it uses time for computation, is kind of a good candidate for the analysis of time series, starting from spiking recurrent neural networks. And time series are used very often to infer information from the recordings of biological signals. For example, from electroencephalogram, you can detect dyspnea, you can detect if the person is coughing, you can detect stress, and so on. And if you can do this with a neuromorphic device using recurrent spiking neural networks, you can go towards the design of embeddable and low power systems. The most futuristic approach suggested in the roadmap is the brain repair. So using artificial devices, using neuromorphic technology to integrate with biological grafts that promote brain repair, but they cannot be controlled. So neuromorphic devices could be programmed and could learn to control how biological grafts can improve the regeneration of damaged brain tissue. For these applications in particular, we need to really improve both the computational side, so how to use neuromorphic computing to extract information from the different signals that the brain, in this case, produces. But also, we need to further miniaturize and decrease the power consumption of neuromorphic devices so that they can be implantable for the different applications. So what I think is the take-home message of the application part is that people are using neuromorphic devices and computation to solve problems that cannot be easily solved with traditional computing. And these are problems where you need to process real data and produce a behavioral decision. And to do so, we need improvements both in the devices and in the computation so that we can deliver the systems that we have in mind. And with this, I thank you for your attention, and I thank also the European grants that have supported this work, and also the write-up of the roadmap, for example, for the Neurotech consortium that is promoting the community of neuromorphic engineering and computation.
Okay, thanks a lot, Chiara, for giving this overview about the field of applications. So please, we are a little bit over time, but it's no problem. There's still some chance to ask questions to Chiara. Please put them into the chat. So perhaps in the meantime, I would be interested in your judgment. I mean, the requirements in order to get, for example, a qualification for a medical product, or also for autonomous driving. I mean, the requirements in terms of getting this into a product are very high. So where would you judge at the current stage, will we see neuromorphic engineering first in a product which you can buy?
This is a very good question. So the first answer is there's now a lot of interest from the big industries. You know, that there is Intel that is developing Jülich for research, but they are investing in neuromorphic computing. There are other big companies that are developing sensors. There's Sony, who bought the Prophecy for developing event-driven vision sensors. So I guess that now there's a stronger push for the application side. In research, we are still, you know, working on the methods and how to develop the computational part, and the fact that there's industry might help the integration of these systems with other systems that are more standard. That's a very difficult problem, because using SPIKE, using a very different representation of information, is preventing us from integrating into systems where there are other parts. And usually applications like automotive, you have a lot of different parts. You don't just have a vision sensor. And so using standardization, using common protocols is required to go towards the real deployment of the systems.
Okay, thanks a lot, Chiara. So due to time reasons, because we really have to finish on time, I ask everybody, to send in questions, and we will answer them afterwards per email. The same is for the recording. We will send it by email. And therefore, I would now like to finally thank all speakers for their great presentations, and the audience for the questions. I hope that this webinar will stimulate the discussion about this exciting field of research and will improve the visibility of the roadmap and the success of this journal. I wish you all a great Christmas time and holiday time and a successful New Year 22. So when we will all be hopefully back to a kind of normal life as compared to the current pandemic situation. So please have a good time, and thanks all for coming and contributing. Bye-bye.